So now we're going to talk about what happens when you have two datums listed in the second line of a composite tolerance, composite position tolerance. So when you're talking about the frame tolerance zone, the rotational degrees of freedom constrained relative to the primary and secondary datum, and then the features, again, must be able to meet the tolerance requirements in both frames. And then here's what that means with two datums. As you can see, we have this 531 dimension coming from datum B, and we're allowed to translate this whole position in this direction here, and we also have to set up on datum A, so we have the location of these holes are also relative to datum A. So now let's talk about what happens when you have two segment feature control frames. Okay, so in this particular case, what we have is we have two feature control frames here. Instead of one composite, we have two feature control frames. So when two position tolerance segments are used, it is not a composite tolerance. The position tolerances are actually applied individually. Here is an example. Okay, so what this means is that this set of four holes has to meet the first set of tolerances, and it has to meet the second tolerances individually. Let's talk about functional gauging now. A functional gauge, and this is the subject of your project. Functional gauges can be used when the tolerance has an MMC modifier. So if you have a position tolerance and it has an MMC modifier, that opens you up to be able to inspect these holes by using a functional gauge. The gauge will have pins that are made to the virtual condition of the hole. Now, I'm talking about holes here, so it's the MMC, which would be the smallest hole, minus the positional tolerance to get to virtual condition. The part must fit over the pins and contact all three of the datum simulators. The fixed diameter pins automatically permit bonus tolerance as the hole size deviates from MMC. That's the beauty of functional gauges. And then the hole size must be specified separately, verified separately. Okay, so you use the functional gauge to inspect the location of the holes, but then you also need to inspect the hole size because the functional gauge does not check the size of the holes. Let's look at this cartoon now. We have a feature control frame here. We have three datums, the back surface A, datum B is the larger of the two second surfaces, and then datum C is the smallest for the tertiary surface. Here is our functional gauge to check this. Okay, so we have the 4 by 208 plus 5 minus nothing. That means our maximum material condition is 208. So if we take the 208 and we subtract from it 32 thousandths, we get a virtual condition of 176 thousandths. So we make this is a functional gauge here, demonstrating how a functional gauge is used to inspect the location of the holes on this part. So we make the 4 pins at the virtual condition. We locate the 4 pins on our functional gauge here at the basic dimensions of the part, the 375, the 500. Okay, so to use this functional gauge to check the part, what I do is I take my part and I put it over the functional gauge. If the pins fit through the holes and datum A picks up the high spots on datum A simulator, and we can touch the datum B simulator at least 2 points back here, and we can touch the datum C simulator back over here, then we know that this part meets the feature control frame for location. It doesn't say anything about the size of the holes. I have to inspect those independently. Okay, so the features of a functional gauge are datum simulators to pick up the datums, one for datum A, one for datum B, and another one here for datum C. And then it has these pins for the holes that are built at the virtual condition of the hole, which would be the smallest hole minus this true position tolerance And remember, to use a functional gauge, we have to have the MMC modifier here. So the MMC modifier allows you to use this functional gauge. And the functional gauge is something that's made to easily check the position tolerance of parts at maximum material condition. So this is how we inspect this feature control frame for true position. Okay, so gauging a composite position tolerance. Okay, so similar to the single segment position tolerance, but two gauges are typically required to check a two segment composite tolerance. So let's look at an example for that. Now, this one over here. Okay, this describes my functional gauge that I was talking about. We have a datum A simulator at this lower surface. We have a datum B simulator at this surface right here. And then we have a datum C simulator at this surface over here. Now, we have these pins that are built at the virtual condition. Okay? And that checks the upper feature control frame of this 32 thousandths. So now that locates the pattern. That locates the pattern of the holes. Now, once we're inside the pattern, we have only 16 thousandths true position. So in which case, we have this second gauge, the second functional gauge for checking the lower segment. Now, if we notice, this virtual condition of the lower segment is a different size than the upper segment because we have a tighter tolerance. Okay, so essentially what happens is this functional gauge here checks the location of the holes relative to the datum surfaces. Okay, and that's done to one virtual condition because it has a looser tolerance. Now this one over here has a tighter tolerance. Okay, but if you notice, the functional gauge does not pick up any datums except A. Okay, so if we look at our feature control frame, only one datum is referenced. So therefore, our functional gauge only has to check to datum A. Now, to use this functional gauge, we would take our part, our manufactured part, we would put it down over these three pins. Okay, the part would have to fit over the three pins, and the part would also have to be able to contact the datum A simulator. If you can get the part over those three pins and it contacts the datum simulator, then the part is good relative to that second lower feature control frame. Again, this is how functional gauges work. They're an easy check for true position. Okay, so let's talk about coaxial hole patterns. This is a tolerance that's typically used for hinges. It often requires close position relationship, and the pattern may have a large location tolerance, and the holes may have different diameters, so it can be tricky. So here is a coaxial hole pattern. Okay, so what we have here is we have a feature control frame like this. It calls out 2 by. When it says 2 by, I've got one hole on this side of the groove and I got another hole on this side of the groove. So it's actually two separate features. So 2 by 378 plus 3 minus nothing, excuse me. And then we have this composite feature control frame. So the holes must be located relative to their datum surfaces within this 16 thousandths at MMC. So then, A, B, and C. Okay, so then, once I have those, the lower frame gives us this tolerance zone here. So we have a 16 thousandths, these two outer lines, that's our tolerance for our upper segment. But once we have those tolerances, we have only one permissible axis for the 3,000th cylindrical tolerance zone for the coaxial hole here. So that's what this 3,000ths means. It actually holds the holes tighter relative to each other. It has to be on this 1/3,000ths diameter axis here. So that's how we hold those holes tighter for coaxial. Here's another concept I want to talk about is radial hole patterns. So what we have here is a cylindrical part. We have a hole that passes through the diameter of the cylindrical part. So we have a datum A here on this diameter. So A to B at maximum material condition. That's our composite datum. And then datum C would be the surface here, which locates. Now, what does this mean in terms of tolerance? If I'm looking at it from the top of the part, I have a 20,000 zone at MMC, and it's centered on this basic dimension here, and it's also centered on the center line of datum A and datum B, and it goes to the center point. So I have this diametrical tolerance zone. It looks like this. That's a radial hole pattern. And then we're not really going to talk about symmetry and concentricity. They're being phased out in GD&T. Position tolerances are a lot more flexible and can be used to control symmetry and concentricity. So in the future, symmetry and concentricity are not going to be part of GD&T. We're just going to use positional tolerances.